So, I hope so that we had completed auto transformer in the last class. If you want me to recall it once again, I'll do that before going over to per unit notation. Now, let us go over to per unit notation. So, in per unit notation, what actually we are going to do is, if we are defining some base impedance in ohms, we are going to define some base impedance in ohms for a particular system. And then we are going to say the present value of impedance that I am having for my transformer primary or transformer secondary, it is how much percentage of that, or what is the fraction of the actual impedance of the winding as compared to the base impedance that I am defining. First of all, we should have some way of defining base impedance. So, if I am going to take a general power system, I am going to look at, first of all, I have to fix 4 values. One is, what is the kVA rating? What is the voltage rating? If I fix these 2, automatically current is fixed and impedance will also be fixed. So, I have basically 4 base values for the system. So, if I have a system with a particular value of kVA defined as its base and particular value of voltage defined as its base, I can say kVA divided by whatever is the voltage in kilovolts will give me ampere directly. So, that ampere will be base ampere, and then whatever is my base voltage divided by the base ampere that I have defined, that will become base impedance. Let us take again, for example, what we had taken earlier also, that is 2.2 kVA, 220 volts by 110 volts transformer. So, when I have a transformer, generally we will define the kVA as the base kVA for both primary and secondary, because the power is invariant in the transformer. Whether I am looking at it from the primary side or secondary side, I am going to have the kVA as a constant basically. So, base kVA is 2.2 kVA itself. This is going to be base kVA. Whereas, this is going to be the base voltage for the primary. Whereas, this will be the base voltage for the secondary. Normally what we do is, for a transformer, we will not define a single base voltage. We will define the base voltage for the primary separately, for the secondary separately, because we are going to step up or step down. kVA is the same, whereas this is going to be defined independently for each of the sides. Fine? So, if I look at the current, I will have the base current for the primary. I will have it to be 2200 divided by 220. So, that is going to be 10 ampere. Whereas, if I look at the base current for the secondary, that is going to be 20 amperes. Right? Now, if I define base impedance very clearly, for the primary and secondary, they would be different. Right? So, base impedance, if I try to look at it, Z base for primary will be 220 divided by 10, which is 22 ohms. Whereas, if I try to define Z base for the secondary, that would be 110 divided by 20, which is actually 5.5 ohms. So, the base impedance will be different for the primary side and secondary side. Similarly, base voltages and base currents will be different for the primary side and secondary side. Whereas, if I look at the kVA, it will be common for all of them. Now, what is the real point of defining per unit? What is the point of really defining all these base and confusing the hell out of you? You can really think that way. So, let us try to look at the utility of it. Okay? So, let me take the same transformer, right? So, let us say I am defining here R1, X1, and this is my primary. I am not unduly worried about RC and XM because I am going to talk more about voltage regulation and maybe more about I square R losses. So, that's the reason why I am looking at mainly the series parameters. Okay? So, I am having this, and on the secondary side, I am going to have R2, X2, and here is my load. Right? Now, if I am connecting a load of 5.5 ohms, what we calculated as the base impedance, under normal operating condition, I should see that the current that is flowing is 100% or rated current. So, if I am connecting 1 per unit of load, what I mean by 1 per unit is same as that of the base impedance that I have calculated. So, if I am connecting 1 per unit load, that means that will correspond to 5.5 ohm. If I am connecting this, the current flowing here will be I2 rated. And I2 rated we said as 20 ampere. Right? Whereas this 20 ampere get translated into the primary side as 10 ampere. And that is also I base. So, whether I am looking at both of them from the primary side or both of them from the secondary side, from either side, I would be able to say as long as I am drawing 100% kVA from the transformer, the current that is flowing is 1 per unit. Either I watch it from the primary side or the secondary side. So, there is no question of transforming from one side to another. I don't have to do that at all. So, many times if you look at the actual values that are given from the industry, they will always give the impedances in terms of per unit. And also, if I try to see that I2 rated times R2 plus JX2, this is the voltage drop that I am going to get. And maybe I should have said again I2 dash rated multiplied by R1 plus JX1. This is the total drop I am going to get in the series parameters of the transformer together. Now this divided by, if I am looking at the whole thing from the secondary side, I will say this is V2 rated. This is what is regulation. For me, this is what is regulation. So, I can call this as voltage regulation. So, the voltage regulation is essentially defined like this. And what I am looking at basically is the current actually that is being taken from the secondary side directly multiplied by the secondary impedances, and current that is translated into the primary side, I have to write of course R1 plus JX1 dash. So, I have to translate everything to the secondary side now because I am talking about everything from the secondary side viewpoint, right? Rather than this, if I had defined everything in terms of per unit, the per unit basically defines everything with respect to its own base. It doesn't really change it in any other way. So, if it is talking about its own base, whether I am talking about I1 rated or I2 rated as the rated value, it will be 1 per unit. It will be 100%. Nothing more than that. So, I am going to write that as 1 per unit. It doesn't matter really. The same way, whether I am looking at R1 dash plus JX1 dash with respect to the base impedance of the secondary side, or if I talk about R1 plus JX1 with reference to the base impedance of the primary side, it will essentially give me the same kind of drop because I am looking at this current also being referred to the same side from which I am calculating the impedances. Let us again take it this way that we are having 20 amperes here. So I have to write this 20 multiplied by, let me just take arbitrarily some value. Maybe this is 3 and this is 4. I am simply taking some large values, it doesn't matter. And if I say this is 20 multiplied by 3 plus J4, that is what is the drop. It's very, very high, agreed. But this is the drop that I am getting probably on the secondary side. And I told you that generally R1 and R2 dash will be comparable to each other. X1 and X2 dash will be comparable to each other. So if I am talking about a similar value coming on the primary side, I have to write this as 3 multiplied by 1 by 2 square. Am I right? Or 2 multiplied by 2 square. I am sorry, not 1 by 2 square. I have to erase this. So this will be actually 3 multiplied by 4 because 2 square, right? Because please understand it is 220 by 110 volts transformer. So if I am saying that both the resistances are comparable, I should have the same 3 ohms on the other side but refer to the primary side. So it will be 3 multiplied by 4 and this will be 4 multiplied by 4. And what will be the current here? Current will be only 10 ampere. Right? So I have to write this as 10 multiplied by 12 plus J times 16. Am I right? Okay. So these two will give me, if I try to look at the voltage drops, this voltage drop is with reference to 110 volts, whereas this voltage drop will be with reference to 220 volts. Are you getting my point? Because one, I am looking at it from the primary point of view completely. So I have to take its own base voltage, its own base current, its own base impedance. And if I am looking at the other one from the secondary viewpoint, I have to take its own current, its own base voltage and its own impedance. That's what I have taken. So now if I am actually looking at whatever is the fraction I am getting, you try to calculate what is the percentage. This will be 20 multiplied by 5 divided by 110, whereas this will be 12 plus 16. How much is it? 12 square plus 16 square square root. How much will it be? 20. So 20. So this will also be 200 divided by 220. So both of them are essentially the same amount of percentage that I am getting with reference to its own base voltage. So when I express the impedances in terms of percentages or per unit, it really does not matter whether I am expressing everything from the primary side, everything from the secondary side, partially I am expressing something from the primary side, partially I am expressing something from the secondary side. Overall, when I calculate it with reference to its own base, I will get ultimately the voltage drops to be, happening at the same percentage values, right? So, this entire thing, what I get as the overall voltage drop with respect to the voltage rated, this is generally known as the percentage impedance of the transformer. So, if I am having, let us say, R equivalent equal to R1 plus R2 dash and X equivalent equal to X1 plus X2 dash. Yes. See, normally in most of the transformers, the primary and secondary will be comparable. You might have been given different values. Even if you are given different ohmic values, if you try to convert that into, its own base, you will see that the percentage values are comparable. That is, one may have 3%, the other might be 3.25 or 3.5%. That's all I'm trying to say. See, originally if you had measured the values in this 220 by 110 volts transformer, I might have had maybe R1. Do you have that problem we worked out? Can you please give me those values, some arbitrary values I gave? Last time we worked out one problem. The same 220 by 110 volts, open circuit data and short circuit data I gave last time. I can assume it is 5.5 ohms, so it is resistance load. If I have assumed 5.5 ohms simply as a resistance, then I can assume it is in phase. It doesn't matter, I2 angle 0. Right? So I am basically talking about the overall impedance is 5.5 ohm. Here, because I have not taken any phase angle, I can assume that it is resistive load. As simple as that. If it is not resistive, definitely you should have included the phase angle. Right? So, what I am trying to say here is, if it is 220 volts by 2.2 kVA transformer, maybe let me say R1 is 1 ohm, whereas R2, what I got, it should be 1 by 4. If it has to be equal, it can be probably instead of 0.25, it can be 0.26 ohms, for example. I am just arbitrarily taking. Similarly, I am taking X1 probably is say 3 ohm. Here I should have had X2 to be probably 3 by 4, that is 0.75. But rather than that, let me take this to be 0.8. It doesn't matter. Okay? So if I take it this way, yes. N1 by N2 the whole square. Yeah, that's why 1 by 4. (220 by 110) is the turns ratio. If I am transferring everything to the primary side, I have to multiply by 4 because 2 square. 2 by 1 the whole square. Always remember, if I am transferring from high voltage side to low voltage side, then it will be 1 by turns ratio the whole square, where the turns ratio is greater than 1 again. Whenever I am transferring it to the higher voltage side, I have to always multiply by a factor which is greater than 1 whole square. So if I am looking at 220 by 110 volts, right, 220 is going to carry lower current. If it is carrying lower current, the impedance has to be larger. It cannot be smaller. So higher voltage side will always manifest larger impedance, and lower voltage side will always manifest, it is going to essentially show higher current, because of which it will manifest lower impedance. So you are going to have high voltage, high impedance. Low voltage, lower impedance. That is the manifestation. All these confusions will be eliminated if you are doing per unit. Because if I look at it here in terms of per unit impedance, we said base impedance in this particular case on 220 volt side was 22 ohms, whereas base impedance in this case was 5.5 ohm. So if I express 1 plus 3, J3, this is what is R1 plus JX1 divided by 22. This is what is the per unit impedance of the primary. And here I am going to have 0.26 plus J0.8 divided by 5.5 is going to be the per unit impedance of secondary. Are you getting my point? Now you calculate the per unit. If you guys have the calculator, please try to calculate the per unit. Both of them should be almost comparable. I'm not saying they will be exactly equal, but they will be comparable. They will not be equal. In fact, ideal transformer, everything should be 0. Ideal transformer, everything should be 0. And only the parallel parameter should be infinity. I reiterate it. Ideal transformer. So if I am going to have an ideal transformer, winding resistances are 0, leakages are 0, magnetizing reactance is infinity, and core loss component of resistance is infinity. Actual transformer, generally I am going to have the primary and secondary impedances comparable. I am not saying exactly equal. They are comparable. So when I write it in per unit, if I try to write this in per unit, this is 1 by 22, that is 3 by 22, whereas this will be 0.26 divided by 5.5. I can multiply both of them by 10, no, 4. I have to multiply by 4. Then I will be able to get essentially the same base, 22 ohms. So 0.26 multiplied by 4 will be close to 1 again. So I can say very clearly that the impedances what I have got, although I have calculated independently maybe, they would be comparable. So just by observing the values, you would be able to say whether you have made any mistake in the calculation or measurement. If for one of them I get 1 ohm, for the other thing 1 per unit, for the other one if I am getting 22 per unit, for example, I know for sure I have goofed up somewhere. So the per unit values give you some kind of estimate or a ballpark values, approximate values, so that looking at them, just observing them, by inspecting them, you would be able to say whether you have done all the calculations correctly. If I look at a transformer, normally the voltage regulation has to be less than 10% in most of the cases. So voltage regulation, again what we are calculating is on a per unit basis, because we are dividing it by rated voltage all the time. So we get the drop and we are dividing it by rated voltage. Because we do that, again we are able to get an estimate whether the voltage drop is less than 10%. That means whether I have done everything correctly or whether the transformer is good enough. All these things I would be able to get a feel for right by observing. That is one of the major advantages of using per unit notation. So generally, whenever we buy a transformer from the industry, they will only say the impedance is so much percentage, that is maybe 0.1 per unit or 10%. This is what they will say. What do you mean by this? For that, I had to get into all this discussion. So what we mean by this is, I rated multiplied by whatever is my Z equivalent in my transformer divided by V rated. Only thing you have to make sure is I rated and V rated, I take it completely on the LV side or completely on the HV side. Similarly, I take Z equivalent also completely from the LV side or completely from the HV side. I better take everything from one side. This is equal to 0.1. That's what it means. The meaning of this is this. Right? Which means, if I know this 220 by 110 volts transformer, 2.2 kVA, when it is carrying a current of 10 ampere on the primary side, I am looking at what is the drop in the Z equivalent visualized from the primary side. And I say that that drop as compared to 220 volts is 10%. So I am going to have this entire thing equal to 22 volts if I am trying to look at it from the primary side, when V rated is 220 volts. Are you getting my point? So this is the meaning of the per unit basically. And most of the industries mention the RC values, XM values and R1 and R2 dash together as R equivalent and X1 plus X2 dash as X equivalent. All of them are mentioned in per unit, hardly ever mentioned in ohmic values. Because if you try to look at the ohmic values, especially for a transformer like 400 volts slash say 4000 or 40,000 volts, you will see the ohmic values grossly mismatching between the primary and secondary. Because it's the same kVA, the current would also be stepped up by 100 factor, 100-fold on the primary side. And the voltage is stepped up by 100-fold on the secondary side. So if you look at the ohmic values, on one side if it is 1 ohm, on the other side it will be 10,000 ohms. Are you getting my point? So it will lead to a lot of discrepancy, and it may be very, very difficult for you, for anybody to understand whether things have been done properly or not. When you express it in per unit, all of them will boil down to same percentage, roughly, because you are using the base voltage as that particular side voltage and current as that particular side current. That's about it. Okay? So in general, per unit gives two advantages. One is, just by observing the values, you can say whether the values kind of fall within the normal range for a transformer, for an induction motor, for a synchronous machine. You should be able to say that, because all of us generally who are familiar with electrical apparatus can say transformers should have impedances less than 5%. And similarly, I should be able to say if it is RC or XM, it will be even more than 100%. Maybe, 200, 300, 400%. Very high values. Whereas, if I look at an induction motor, I can say normally the impedances, series impedances will add up to 25 to 30%. So, roughly we have the ranges for different machines. So, by just observing, we would be able to say whether the ranges are falling or the values are falling within the range. That's the first advantage. Second advantage is, you can just calculate the values from either of the side. No problem. You don't have to transfer one ohmic value from one side to another. Everything that will be given will be normally in percentage, which will be common for the entire apparatus, whether you look at it from the primary or secondary. So that's the major advantage of per unit, right? One of the problems in the tutorial sheet, I think, had given percentage impedance is 10% or something like that, which actually indicates this. I rated times Z equivalent divided by V rated for any side, whichever side it is 0.1. That's what it means. So similarly, I should be able to say I rated square multiplied by R equivalent divided by the overall kVA rating will give me percentage resistance. I am only writing this. See, we wrote I rated multiplied by Z equivalent divided by V rated as percentage Z equivalent or per unit Z equivalent. I can similarly write I rated multiplied by R equivalent divided by V rated will give me percentage R equivalent. Instead, I can multiply and divide by I rated. So what I will get will be I rated whole square multiplied by R equivalent divided by kVA basically, because V rated multiplied by I rated is kVA. So this also will give me per unit resistance. I think one of the problems gave this. At rated condition, the ohmic losses were so much percentage of the overall kVA rating. It was given. The rated copper losses were 5%, 2% of the rated kVA. That means essentially R equivalent is 2%. That's all. Right? The same way, I should be able to write I rated times X equivalent divided by V rated will be equal to percentage X equivalent. Right? So much so for the per unit notation. We use it all the time in the industry, so that's all the more reason You guys should know definitely how per unit notation is used, what is the significance of it, why it is being commonly used all over the industry. Yeah. See, if I am calculating separately for the primary and separately for the secondary, if I am trying to write Kirchhoff's laws, how will I take that into consideration? What I have to do is to write two loop equations and step up or step down the voltages and currents every now and then. I wanted to actually mention the whole thing as one single electrical circuit, if it is possible, which will actually give me ease of calculation. That's the only reason why we are transferring over all the parameters to one single side, so that I will be able to write one KVL equation, one KCL equation, and I would be able to calculate the whole thing. That's the only reason. In per unit notation, we can definitely write about the core losses. If at all core losses in this case is something like 100 watt, I would say 100 divided by 2200. Whatever I calculate as per unit, I can say this is the core losses in per unit. That's it. You can again do it in terms of kVA, no problem. Yes. Per unit Z equivalent and voltage regulation at unity power factor at 100% load. Yes, yes, that's right. His observation was Z equivalent in per unit and voltage regulation in per unit, are they equal? Yes, they are equal, provided you calculate it at unity power factor. No, not unity power factor. Will it be unity power factor? Because 1 and 0. Not really unity power factor. At least 100% load is for sure. Okay? Because you are looking at R equivalent plus J X equivalent multiplied by I. Whatever is the I value, and you are not really considering the power factor angle there. So, we are assuming probably the power factor angle to be 0, but we are not neglecting the vertical component, what we talked about. If you may recall, we drew the phasor diagram and we said this is V2 and there is some addition like this, and then we are getting this as V1 dash. And then we said this vertical component we are neglecting. Remember, that vertical component we should not neglect. So it will give you more accurate regulation actually. I times Z equivalent, what you are getting is a very, very accurate regulation at rated current at unity power factor. That's what it is. Yes. So in one sense you can say Z equivalent is indirectly giving you the voltage regulation, but at rated current. At rated current. Clear. Before we venture into the three-phase transformer, right? Let us try to just take a quick look at current transformer and potential transformer. That will complete our discussion on single-phase transformers. Okay? So let us try to look at one of the special transformers which is known as instrument transformer. The name instrument transformer comes from the fact that this is being used for measurement and instrumentation. Invariably, measurement and instrumentation go hand in hand, because you may measure something, you may try to step up or step down, you may try to do some manipulation with it, and then you may try to ultimately see whether, you are able to follow whatever is the required pattern. For example, you take an air conditioning system. Maybe you want to have the temperature always fixed at 27 degrees. So, you might try to continuously measure what is the temperature. For that, you might have some kind of temperature sensor. That temperature sensor invariably will convert that into some voltage, because invariably most of our control system components are electrical in nature. So, the temperature will be converted into an equivalent voltage. Then that will be compared with a reference which is corresponding to 27 degree, that will also be probably a voltage signal. So I'll compare the two. If the temperature has not reached 27 as yet, it is at 30 degrees, then probably I'll have to turn on the compressor within the air conditioning system for quite a long time. So that compressor is going to be on for maybe as long as the coolant is compressed and then it is expanded and then it goes through the heat exchanger and overall temperature comes down to 27 degrees. This is going to take place until the temperature reaches 27. After it reaches 27 also, continuously it is going to compare it, right, with the actual reference temperature. So if the compressor is off for too long, then again you might have to start the cooling cycle. So this instrumentation is done maybe with the help of some of the apparatus called transducers, but we are not going to get into that, but we are essentially looking at if I have to control some voltage or current. So voltage control, if I have to do, I might have to measure the voltage, check it out whether it is as per what I need or what my motor needs. This, if it has to be done in AC system rather than in DC system. DC you can't use transformer, obviously. But if I am looking at some AC system where I have to measure thousands of kilovolts, I may not have a voltmeter to measure that kind of voltage so easily. So what I am going to do is, let us say these are the two terminals across which I have to measure the voltage. So this is the V to be measured. Now what I am going to do is to connect a potential transformer. I will call this as PT, potential transformer or voltage transformer, and I am going to actually connect across these two terminals itself my potential transformer. And the potential transformer should offer really very large impedance. If it offers a small impedance, it will be as good as short circuiting the two terminals to be across which I want to measure the voltage. So this potential transformer should essentially work similar to a voltmeter. A voltmeter generally offers a very large impedance. So similar should be the case as far as the potential transformer is concerned, because of which the secondary of the potential transformer will always be open circuited. It cannot be ever short circuited, or it cannot be ever connected with a tangible small value of resistance. No way. It should not be done. It should always be open circuited normally, and I may connect a voltmeter here. At this end, I may connect a voltmeter which will measure what is the RMS value. What I am doing is to bring down the voltage from a very large value to a range where my voltmeter will work. So I may not have voltmeters available for hundreds of kilovolts. So I may have this as 1000:1 or 500:1, for example, as the range. So because of which, if I am having 500 kilovolts, I would be able to step it down as 1 kilovolt, and I would be able to measure this with the help of a voltmeter. So I am essentially trying to use the services of the voltage ratio of a transformer so that I am able to bring the voltage down to the range where my voltmeters would work. But in the process, I should not be drawing excessively large current from the supply. I cannot do that. That is the reason why I am keeping this as open circuit. Keeping this as open circuit ensures that only whatever is the voltmeter impedance is transferred over to the other side. Of course, with the turns ratio. So it is going to be really a large impedance. It is as good as you are not drawing any current through the voltmeter or through the potential transformer. So potential transformer will always have higher number of turns towards the side from which I want to measure the voltage and much lower number of turns towards the other low voltage side. And low voltage side invariably will be open circuited. It cannot be connected even with a smaller value of resistance. So in this case, if I may call this as V1, if I may call this as V2, I'm going to have V1 by V2 equal to N1 by N2. But I cannot write this is equal to I2 by I1 because it is open circuited. I'm not going to have any current on the secondary side, literally. Yes. Yes. Impedance of the voltmeter generally will be of the order of kilo ohms or even more. And that kilo ohms multiplied by N1 by N2, the whole square, will be visualized by the source whose voltage I am measuring. Which is fair enough. It is going to be really, really large. That, see, again, large or small are relative. I hope you understand. How do I guess whether the impedance is large enough or not? That is where the per unit is very useful. If I say this potential transformer is going to be of 1 volt ampere rating, but it is going to be 500 kilovolts divided by whatever kilovolt it is, 1 kilovolt. Then I can definitely calculate what are all the base impedances. Compared to the base impedance, the voltmeter impedance has to be quite higher. Then I am fine. See, if I don't open circuit it, if I am going to connect a resistance here, okay, this will draw a current. If this is drawing a current, this will also draw a current. What I want to do is only to measure the voltage. I don't want to load the source. When I'm drawing current, I'm loading the source. Am I not? I don't want to do that. That's all I'm trying to say. When you connect a voltmeter across your electrical circuit, what are you trying to do? You are just measuring the voltage. You don't want to connect your voltmeter as a load, do you? So, if you don't want to load it, you better not draw a tangible current. The current drawn should be as minimum as it can be. So I am telling that it has to be as good as an open circuit. That's all. Got it? Yeah. So this voltage current relationship cannot be applied in a potential transformer because I am keeping the secondary side as open. The primary side will have no load current. Secondary side has literally zero current. So under open circuit condition of any transformer, V1 by V2 equal to N1 by N2 is valid, but that is not equal to I2 by I1. Okay? The other counterpart of this is potential transformer, the next one is current transformer. The current transformer is being used for measurement of current, high currents. So let us say I am having a conductor through which maybe 10 kiloamperes of current is flowing. And I want to measure this current. It can be a variable current. The maximum is probably 10 kiloampere. Minimum can be as low as 100 ampere. Let us say. I1 is no load current. I2 is 0. Under open circuit condition. Then how can I write the ratio? 0 by I0. Doesn't make much sense. I1 will not be 0. I1 will be no load current. I hope you understand. Open circuit condition of a transformer, you will have no load current. It will not be 0 current. Right? So I can't write this is 0 by 0. It is rather 0 divided by I0, which is the no load current. So it doesn't make sense. That's why that relationship is not holding good, especially when the transformer is under open circuit condition. Got it? Let us look at the current transformer. So let us say I have 10 kiloampere of current. It is a variable current. Maybe it changes from 10 amperes to 10 kiloampere and I want to measure this. For measuring this, I can use this itself as the primary. Very often, current transformers use the conductor whose current needs to be measured itself as the primary. You don't have to have a separate primary at all, in all probability. And what we normally do is, around this, we put a toroid. You guys know what is a toroid? Toroid is like a bangle around which I am going to wind many turns, basically. So that is also a laminated core, which is like a bangle, and then I am going to put huge number of turns around it. So in this toroid, which is actually around this coil, I am going to make huge number of turns. These are the two terminals that are available. Now, this is essentially going to make the turns ratio as this is N. This is no turn at all, which is 1. One conductor means it's counted as one turn. So it is going to be 1:n is equal to 10 kiloampere, rather 10 kiloampere is to the current to be measured. So let me call this as I2. Yeah? See, this conductor is taken as one single conductor, which is actually equivalent to one turn. Because the return you don't know where it is. And around that you are having a toroid which has n number of turns. Right? So obviously the current what I get here will be 1 by n times whatever is the current that is actually there in the conductor. Fine? So it will be clearly, step down. But here, if I leave it as an open circuit, the voltage induced will be enormously high. So I can never leave the current transformer as an open circuit. Instead, I should connect a small resistance. How small is small? That depends upon, again, the per unit. If you calculate what is the base impedance compared to base impedance, make it really, really small. So I'm going to have 1 by n equal to, I2 by I1. Is that so? Yeah, I2 by I1 or I primary. But that is not equal to V1 by V2. Because I'm going to literally short circuit the secondary. Literally, I'm going to short circuit the secondary, because if I don't short circuit it, if I am having in 10 kiloampere current, if I have even 1 volt, it will be translated as maybe 1 multiplied by n volts. N may be 10,000. So I will get 10 kilovolts. And if I put my hand there by any chance, I really had it. So we have to be really, really careful, because the insulation may not be able to withstand that kind of voltage. Got it?